nuclear equations, you're going to be asked to find like the missing part. So here in this first one, I guess we can call it number 1 here, you're looking for the blank. Now on each side of the equation, even though we're splitting up, so like we have uranium over here on the left side, but we don't have it on the right side. So it's a reactant, but it's not a product, right? Like we have it on one side, but not the other. However, the masses have to equal each other. And I know mass defect, like a little bit of the mass disappears. But we don't account for that when we're doing reactions because it's such a small amount that actually turns into energy. So the mass numbers need to equal each other on both sides of the arrow, and then so too the atomic numbers. So you can think of the arrow as sort of like an equal sign. So I'm going to add up the top over here. So 235 plus 1 is 236. So that means on this side of my arrow, I need to have 236 as well. Well, I have x, I don't know what that is because that's my blank, plus 90, and then plus the 2, the coefficient 2 gets multiplied by the 1, so I have 2. So then if I solve for x, my mass is 144. So I'm going to do the same thing with those bottom numbers now. On this side, I have uranium 92 plus the neutron, which is 0. So I have 92 down here. So that means on this side, I need 92 as well. So 92 is going to equal x. I don't know what's on the bottom there. Plus 37 from the rubidium. And then plus 0 from the neutron, because the 2 times 0 gives me 0. So again, solving for x, I get 55. Now I'm going to go over to a periodic table. And I'm going to look up atomic number 55. So it is right here. So cesium, CS. So I'm going to go back, and my answer, or my symbol becomes CS. So this is my actual answer for this problem. The particle that was missing was cesium. It might be, if I had had like a 4 and a 2, right, I would have had to recognize that that was an alpha particle, so I would have been missing an alpha particle. If I had like a -1 and a 0, I would notice that that's a beta particle. Whoops, I got that backwards. If I had a 0 and a -1, that's a beta particle. If I had had a 1 and a 0 missing, that would have been a neutron. If you ever get like 2 and 0, N, what that actually means is 2 and 1 over 0, because we don't actually, this doesn't exist, right? It means this. So it just means you have 2 neutrons. So you do need to be able to recognize what that is. But when you get numbers like 144, even like 90, really if they're bigger than like, I don't know, like 12 probably, because you could maybe have 3 alpha particles. So if you had 3, that would give you a mass of 12. But really, once you get up into higher numbers, it's not going to be a particle. It's going to be an actual element. So that's how you do these. I'm going to do one more example. I'm going to do number 2 here. So on this side, I have 236, and I'm going to solve for x. So I have 236 needs to equal 152, plus I don't know what x is, and then plus 3, right? 3 times 1 is 3. So that equals 81. So I'm just going to write it down here. X equals 81. And then I'm going to do the bottom, so 92. And then I have 92 equals, I have 60 plus x, and then again plus 0. Why did I write 92? Oh, because that's what it equals, sorry. Okay, so 3 times 0 is 0, so that's how I got 0. So 92 minus 60 is 32. So I'm going to go over to my periodic table. I'm going to find atomic number 32, and that's germanium. So I'm going to go back and put a G, E. You always look it up by this number, right? The atomic number. We looked up germanium by that number. We looked up cesium by the 55, right? The mass number is protons plus neutrons, which is this top number. That does not appear on the periodic table. Again, you're looking it up by the atomic number. So my answer here was germanium, 81. The other type of problem you're going to see is like this one down below. This table is actually on your worksheet, so I'm not going to do every single one, but I just wanted to show you guys through an equation the difference between fission and fusion. So here I have a nucleus of 92, and then all my nuclei on this side are 54, 38. So it got smaller. So that means it is fission. So like I said in the notes, it kind of like fizzles out. Remember, fission is getting smaller and then fusion is getting bigger. So here's an example of when fusion gets bigger. It's 2 and 2, so 2 small ones. And then here I have it all combined into 1, right? A mass of 4. And then here, these were masses of 3s. So I have like a bigger one here, even though it happens to be the same element. I have a bigger combined element. So that's why this one is fusion. So these two were actually on your worksheet. So are these two, so you can do this two on your own. But please let me know if you have any questions.